Hello and welcome to the presentation of my undergraduate thesis, Elevator Health Monitoring using an Inertial Measurement Unit. First, here is an outline of the presentation. First, we'll talk about the introduction, then the objectives, then the methodology of the research, then we'll talk about the results and discussion, and finally the conclusion and the future works. Elevators have become an essential amenity nowadays. The most common type of elevators are the geared traction type of elevators. The geared traction type of elevators comprises of many mechanical components which need periodic maintenance and inspections. Without periodic maintenance and proper inspection, some common problems of an elevator are faulty motor, faulty brake control equipment, faulty car leveling mechanism, overspeed, underspeed, overtravel, poorly functioning buffer, corroded guide rails, derailed car from guide rails, and uneven acceleration and retardation. Therefore, Bangladesh National Building Code recommends a maximum inspection interval of 6 months. However, inspection of an elevator is not an easy task. The problems of periodic inspections are: it's a tedious process, it requires shutdown of operation of an elevator, and requires a backup elevator to carry passengers in the absence of the main elevator. It also requires the dismantling of the elevator and requires expert technician to carry out the inspection process. Therefore, in this study, we have tried to use an inertial measurement unit to inspect the health of an elevator by generating the acceleration profiles in all three directions of an elevator which is descending from 5th floor to ground floor with the use of an onboard low-cost inertial measurement unit. Then our objective is to denoise the raw acceleration data with an appropriate filter and then analyze the filtered acceleration profiles to find the different qualitative and quantitative parameters of the elevator motion. Here's the elevator used in this study. The manufacturer of the elevator is Schindler and the capacity of the elevator is 1050 kg or 14 persons. This elevator is situated in Mechanical Engineering Building of Bangladesh University of Engineering and Technology. Here's the sensor used in the study. The sensor is MPU 6050 3-axis accelerometer and gyro sensor. It communicates on I2C and has a programmable dynamic range. However, we used the dynamic range from -2G to +2G for the greatest sensitivity. And finally, for this study, the error of the sensor was maximum 3%. One important aspect of an accelerometer is its orientation and calibration. The coordinates of the sensor body is called the body frame, and the coordinates of the surroundings is called the inertial frame. However, the sensor frame of reference is not always aligned with the inertial frame. Therefore, the usual method is to find the offsets of the body frame from the inertial frame and subtract the offsets from the readings to convert the body frame readings to inertial frame readings. However, this method is not applicable for our application and study, because since we want to find the acceleration in the x direction, y direction, and z direction of an elevator car, the sensor has to be aligned perfectly with the inertial frame of reference. We know that there is always a constant acceleration of 1g, that is 9.81 meter per second square, acting downwards on the Earth's surface. When a sensor is randomly oriented, it picks up the components of this gravitational acceleration in all three directions. By vector addition, we can find the original value of gravitational acceleration, that is 1g. If the sensor is randomly oriented like this inside an elevator, when the elevator will start moving vertically, it will pick up the vertical acceleration of the elevator in all three directions. Therefore, we cannot distinguish the lateral acceleration and vibrations with this orientation. Now, if we rotate the sensor along the y-axis, the x component becomes 0, and if we rotate the sensor along the x-axis, the y component becomes 0, and the sensor completely aligns with the initial frame of reference. This distinct orientation will help us to distinguish the lateral vibrations from the vertical acceleration. Here is the electrical connections of a setup that we used to self-calibrate the orientation of the sensor. This is the self-calibrating double servo setup, which has 2 degrees of freedom, which is built for the self-calibration of the sensor. Here, servo 1 rotates the sensor along the x-axis to make the y component 0, and servo 2 rotates along the y-axis to make the x component 0. Here is a demonstration of this double servo setup working. A PID controller takes in the x component and takes it as an error and sets it to 0. And another PID controller takes the y component and sets it to 0 by rotating the servo 2. By using this PID controller, we can self-calibrate the orientation of the sensor and align it perfectly with the inertial reference frame. Here, now we can see that the sensor is perfectly straight and oriented with the inertial reference frame and giving the reading of 0.97 g in the z direction, which has a 3% error. Now for the data acquisition. First, we'll mount the setup on the floor of the elevator. Then we'll run the calibration scheme that is shown in the previous slides. Then we'll set up the I2C communication. Then we'll read the MPU 6050 registers and convert the raw values of the registers to acceleration values in G's. When we plot the acquired raw acceleration data, we can see that there's too much noise. Therefore, we have to use an appropriate filter to find any distinct acceleration profile from the readings. We have used 2 filters in our study. The first one is the Savitzky-Golay filter, which is also known as SG filter. It takes a window size of twice n plus 1 from the whole data set and fits it with a polynomial order of n to find the filtered point. Here we can see an animation of the SG filter working. Now for the results. After applying SG filter in the acceleration in the x direction, we can see the results after taking window size of 21, 51 and 201. However, the window size of 21 is still too noisy, and window size of 201 smoothens the data too much. Therefore, we'll be taking the window size of 51 as the optimal filtered profile. In the y direction, we can see that similarly the blue line, which is window size of 21, is still too noisy, and the window size of 201 ignores the small peaks of the graph. Therefore, we will be taking window size of 51. Here it is notable that the filter is used for polynomial order of 3. Now for the z direction, the window size of 21 and 201 are not acceptable. The window size of 201 ignores the small peaks during the acceleration and retardation. Therefore, it is discarded, and window size of 21 is noisy as usual. Therefore, we'll be taking window size of 51 as our filter profile. The other filter that we have used is the Kalman filter. The Kalman filter uses a predicted state estimate from the mathematical model of the system and the measurement from the sensor to find the optimal state estimate of the system. If we assume that the error of the mathematical model follows a Gaussian distribution, then the blue dome depicts the probability density function of the predicted state estimate. And if we assume that the measurement noise follows a Gaussian distribution, then the orange dome is the probability density function of the measurement. By combining these two probability density functions, we get a optimal state estimate with a smaller covariance, which is shown in the gray line. Here are the system models used for the predicted state estimate of the system in the Kalman filter. Here are the initial conditions of the Kalman filter. Here, Pk is the error covariance matrix of the state estimate, Q is the error covariance matrix of the process noise, and R is the error covariance matrix of the measurement noise. However, unlike R, which is the measurement noise, we cannot determine the process noise. Therefore, we'll use trial and error and see which value of Qxy and Qz gives us the best filter plot. Now for the results. In the x direction, when we apply the Kalman filter with 3 process noise covariances with tan inverse 2, tan inverse 3, and tan inverse 4, we see that the tan inverse 4 gives us the best filter plot, which is the black line. In the y direction, we used the same process noise covariances, which are tan inverse 2, tan inverse 3, and tan inverse 4, and here also tan inverse 4 gives us the best filter profile. However, in the z direction, we have used different process noise covariances, which are tan inverse 6, tan inverse 8, and tan inverse 10. However, here we see that tan inverse 10, which is the black line, doesn't give us a good filter plot. It gives out some unreal data because the lower the process noise covariance is, the more the Kalman filter depends on the mathematical model than the measurement. That means the Kalman filter relies more on the mathematical model than the measurement. Therefore, the black filter plot gives an unreal sense of peak. Therefore, we'll be taking the filter plot with tan inverse 8, which is the red line. Now, a comparison between the SG filter plot and the Kalman Filter plot. Here we can see that in the x direction, the SD filtered and the Kalman Filter plots are almost the same. In the y direction, the SD filter plot gives out more peaks than the Kalman filter. In the z direction, it is noticeable that the Kalman filter plot gives sharper and higher peaks than the SG filtered plot. Now we'll use the Kalman filter plot in the z direction with process noise covariance of 10 inverse 8 to find different performance parameters of an descending elevator. Since the elevator is descending from 5th floor to ground floor, we can see that T1 here is the stationary time before the travel, T2 is the acceleration time from 5th floor to downwards, T3 is the constant speed time, T4 is the deceleration time, and T5 is the stationary time after the trip. Here we can notice that the peaks in the acceleration and retardation is not even. Therefore, this elevator has some problem during acceleration and deceleration, and it might create an uncomfortable experience during those times. From this graph, we can see that the maximum acceleration is 0.88 meter per second square, and the maximum deceleration is 1.18 meter per second square. We know that any acceleration beyond 1.2 meter per second square create discomfort. Therefore, this elevator is within range of comfortable acceleration. To calculate the travel time, we'll have to add T2, T3, and T4, which are the accelerating time, constant speed time, and decelerating time. From the graph, we get that the travel time is 15.43 seconds. For the rated car speed, in which the elevator moves during the constant speed time, can be found from integrating the area under the curve during acceleration. By integration, we find that the rated car speed is 1.6 meter per second square. Now for the conclusion. In this work, we have studied the performance of an MPU 6050 as an inertial measurement unit, as it's both low cost and easily obtainable. The acceleration readings along the 3 axes of a moving elevator has been taken and 3 axis acceleration profiles are generated. 2 different filters have been implemented and their results have been compared. And based on those profiles, different parameters of the elevator has been extracted, and also uneven acceleration and retardation has been detected. The future work for this project could be developing a complete framework to run real-time diagnostics of an elevator from the IMU sensor readings of a smartphone. That's all for our presentation. Thank you for your patience.